Hi everyone. Today's topic is type inference. Infer, predict, guess. 유추하는 거예요. 이게 뭘까? Type inference. Until now, when we had like a function expression for a parameter, when we introduce a name, we asked the programmer to write down the type of this parameter. As a programmer, do you like it? I don't like it. I'm lazy, and I think laziness is the virtue of programmers. We do not want to do that, the thing that can be automated. If a compiler or the language system can infer the type, I don't want to write it down by myself. That's type inference. There are going to be several questions and answers again. What is the type of the following expression? What is it? It's a trick question because, as I said before, we asked for the type annotation for x. It's not an expression in our typed language because the parameter x, the argument type, is missing. It's not given. But you know that, or you hope that has type num, right? Why? Because we are adding 1 to that thingy. We are adding 1 to that thing. It would better be a number, not a closure or what else, something else, right? So we infer that we hope that that's num, meaning that the parameter type is num, the result is num, so the whole expression is num arrow num, right? That's the usual way. So type inference is the process of inserting type annotations where the programmer omits them. Programmers may want to write down type annotations, right? But when the programmer omits them, programmer가 type 쓰지 않으면 insert the type annotations. That's how we can perform type inference. So we will use explicit question mark in this lecture, in this talk, to make it clear where types are omitted. In real languages, when types are inferred, we do not need this colon question mark. Then what's the point? Yeah, we are lazy. We don't want to write that. But in this language, to make your life easier for your exercise or homework, right? So we just use this colon question mark to annotate, to denote that it's missing. It's just like lambda x dot x plus 1. Yeah, access type is missing. So the type language tau, right? Type expression tau is num, bool, string, whatever primitive types, arrow type or productive type, whatever constructive types, and question mark. We don't know what it is. You'd better infer that for me. That's it. Okay, let's see some examples. What's the type of x? We don't know. So, in the beginning, let's give it some variable. T1, type variable. 미지수예요. 변수. x의 타입은 몰라. T1이라고 해봐. 그리고 나중에 풀어. We are gonna set up equations. 방정식을 세울 거예요. We are going to set up equations with unknowns. Right? T1 is unknown, and we'd like to know what the type of T1 is. What the value of T1 is. Okay, so we know that X's type is T1, something. X type is something. 1's type is number. X plus 1 should be number, right? So we can infer that T1 should be num. So far so good. Then parameter type is num, body is num, so the function expression has type num arrow num. Cool. So to do this type inference, we create a new type variable for each question mark. Whenever we have question mark in multiple places, we give them different type variables, T1, T2, T3, like that. Change type comparison to install type equivalences, meaning we are going to set up equations. Explanation is going to be helped with some code examples. Let's see. Again, let's look at the body expression. True is Boolean. 1 is a number. X, we don't know, so let's give it an unknown T1. And what do we know? Yeah, this if expression, it's not if 0, it's if. So this one should have type Boolean, and true branch and false branch should have the same type. This is num, so T1 should be, right, what? Num. If the whole expression has num and this is num, then the function expression is again num, arrow, num. So far so good? Then, I told you we are setting up equations. 방정식을 푼다고 그랬어요. Equations with unknowns. 변수가 있어. 그럼 방정식 풀 때, when you were high school students, do you remember 부정 and 불능? Right? When you have equations, when you solve them, there could be cases with no answers. There could be cases with many answers. We're going to talk about each case now. Type inference with impossible cases. 불능이죠, 불능. Impossible cases. Let's see. If x, okay, x's type is t1. That's t1. 1's type is num. X's type is t1. The thing is, it's if expression, and that should be Boolean. And because true branch has type num, this one should be num as well. So this T1 should be both bool and num. There's no type like that. There's no type which is bool type at the same time num type. That's empty. So no type. Meaning that this expression is ill-typed. 타입이 아주 이상해요. It's a type error. T1 cannot be both bool and num. That's impossible cases. In such cases, it's going to be a type error, right? How about many cases? 부정, right? Let's look at that. X's type is T1 and body's type is T1. So the type of the function expression is T1 arrow T1. What is T1? Yeah, I don't know. All I know about this function is I don't know what the parameter type is, but I do know that return type is the same as the parameter type. So it can represent many types. It's a general type, and we can make some instances of them like this. More than one type works. If T1 is num, num arrow num. If T1 is bool, bool arrow bool. If T1 is num arrow bool, it's going to be num arrow bool to num arrow bool. Wow. So the type checker leaves variables as they are in the reported type. If your language type system is pretty, it's going to say alpha arrow alpha. For all alpha, 8. I love Greek letters. So for all alpha dot alpha arrow alpha. Yeah, whatever that type variable type is, it's gonna be the same type for the parameter and return type. And we can instantiate, we can replace alpha with whatever type. Now let's talk about function calls. How can we infer types for function calls? What do you think? This is function part. This is an argument part. And this one we just saw, T1 arrow T1. How about this one? We saw this before. That was the first example. Num arrow num. Meaning that the argument expression has type num arrow num. So it's gonna be bound to this parameter, which is T1. So T1 is gonna be num arrow num. Then okay, the type of this one is num arrow num to num arrow num. This one is num arrow num. So the whole thing is num arrow num, right? Do you see that? You should be able to do that by yourself. No surprise. How about this? It's a function expression, and the body is function call. So x is T1. X type is T1. 7 is a number. Yeah, I know. How about function call? All we know is that x should be some function type. It's going to be an arrow type. But we don't know its return type. Yeah, luckily we know it's parameter type, but we don't know the result type. So let's give it another unknown T2. Then the type of this function part is going to be num2 T2, right? Num2 T2. Then the function expression, what's the type of it? It's what? T1 arrow T2. What is T1? Num arrow T2. So the type of the whole expression is going to be num arrow T2 to T2. Are you with me? Yeah, it's not that difficult. It's just collecting evidence and then solve them, right? So in general, create a new type variable for the result of a function call, just like we did with this one. So create type variables for parameters and function calls and set up equations like that and solve them. Another problematic case, cyclic equations. 방정식을 세웠는데 돌고 돌아. What is it? It's a function expression. Parameter has type T1. T1. Everything is T1, right? The function part has type T1. Argument part has type T1. Then this one is gonna be an arrow type, which it takes T1 and produces what? We cannot solve that in our simple type expressions. Actually, we can extend our type language and so that it can be really expressive. Then we can, describe many things. You can even represent the cyclic types. Like instead of lambda, use mu and like recursive types, but we are not going to talk about that in this semester. If you are curious about that, if you are interested in that, just send me an email. I will give you some pointers. So T1 cannot be num type, T1 cannot be bool type, T1 should be some function type because, it's a function position of function call, but T2 must be T1. It's a cycle. We cannot solve this problem. Cyclic equations. So what can we do? We're going to reject that. In order to reject these bad types, we are going to have occurs check. Occurs check meaning that when installing a type equivalence, when we set up equations, right, make sure that the new type for T does not already contain T. Meaning that when we set up equation, like if, say, true, X, and num, what do? True is Boolean, that's good. X is T1, that's good. And num 3 is num. Then we say that true branch and false branch should be the same. So T1 should be num. This is kind of an equation that we set up, right? And when we set up equations for this expression, which expression? The given expression, X's type is T1, X's type is T1, that's T1, and T1 should be an arrow type, and like that. When we set up equations, if T1 should be what? T1 arrow T2, and that should be the same with T1, meaning this type should be same with this one which contains itself. There's a cycle, right? So when we set up equation, if T1 occurs in this type, reject that. That's a problem. That's occurs check, and we are going to come back to this occurs check when we implement this type inference later. And this is the language for today. TIFAE. FAE with types and type inference. I for inference. So we have the usual FAE, recursive function and conditional expression. So the expressions remain the same. TIFAE has the same expressions with TFAE, right? Because I is for type inference. I is for type inference, not for the others. I is for type inference, so it only matters for types. So the only ready thing is this one, meaning that type is either number, no boolean here, arrow type, or we don't know it yet. Question mark. Question mark meaning missing position, right? So here lambda expression, function expression still has parameter with type annotation .e. And that type annotation could be number or arrow type or question mark, right? If it was num, then programmer wrote that. If it was t, arrow t, then programmer wrote that. If it was question mark, programmer didn't write it, and in order for the expressions to have the same form, right, same syntax, we just require that to be question mark. Are you with me? Meaning that this language TFAE allows programmers to write down types or mistypes. 그래서 이거 잘 아셔야 돼요. 이렇게 썼기 때문에 프로그래머가 파라미터의 타입을 annotate 해도 되고 안 해도 되는 거예요. It is okay both ways. Either put the type annotation or not. So if you know the types, then you may want to write it. If you are lazy or if you don't feel like it, you can omit it. Then this type system will infer that for you. That's cool. Then, the type is either num t or arrow t or question mark. How can you implement that? Type is gonna be either num t or arrow t. Yeah, the usual thing is, or var t. var t. Type variable t1, t2, ... In the abstract syntax, we wrote that as question mark. When we infer types, we had to set up equations with unknowns. 방정식을 세워야 돼요. 그 방정식이 변수예요. That's var t, right? Because we don't know what it is. And when we know what they are, one more time, when we have if x 42 minus 7, this one is going to be I and lambda x colon question mark, right? In the beginning, that's going to be t1. Here, condition position, that's going to be a boolean, right? Not in this TIFAE, but with some boolean value. Yeah, then what can you say? The T1 should be bool type, bool T. So in the beginning, it's gonna be none, right? So this var T, in the beginning, it has no information, so none. But when it has these kind of information by what? Inferring types, comparing types, setting up equations, and solving them. And then we need to put that information into here, so that's gonna be var. Are you with me? Yeah, because var t is usually in the beginning t1, t2 like that, unknowns. So it does not have any information about its time. But later it may know that. So we need to make it var so that we can change the value from none to some. Do you see that? Yeah, let's see concrete examples. That's going to help you understand this better with some cases of var t. As we already saw, type is a trait. Type is either num t, arrow t, or var t. So var t is what? That's just type variable, right? We don't know what it is. We don't know what that represents. So in the beginning, it's going to be var t with the simplest thing, none. Var t none is just t, right? When we say in Scala, val t equals var t open none close, what we are saying in type inference or in the rules is tau is t. Okay, now that we compare those t's and booleans and num types and things like that, we may have some information that we need to replace that with that information like this. Hey, you know what? This t is, it's some type variable. And if you want to know what it is, it has information. It's num t, by the way. Meaning that this type tau is type variable, meaning it's not num t in the beginning. It's not arrow t. It's just type variable t. But we know something about this type variable t, which should be num. Okay, are you with me? Yeah. One more thing. Then, when do we get those information? Yeah, we can compare them like this. One more time. If true x or 8, then this is boolean. Okay, this is t1. This is num. Then we need to make them same. So T1 should be num. That's the equation, right? Right? If we have this lambda x colon question mark dot, lambda y colon question mark dot, if false, and x and y, what can we say? X's type is T1, Y's type is T2. If false boolean, okay, X's type is T1, Y's type is T2. True branch and false branch should have the same type, so T1 should be the same with T2. That's this case. T1 is some type variable T1, but you know what? I know that type should be T2. Oh, really? Okay, then T2 is what? Another type variable. Then what we are saying is T1, tau1 is var T, don't type T1, but at the same time, right? T1 should be T2. Okay, what is T2? Another type variable T2. Okay, last example in this slide is what? Tau1 is, it's some type variable T1, which should be the same with tau2. Just the same, right? Tau1 is T1, which should be the same with tau2. Then what is tau2? Tau2 is, again, some type variable T2, but now this time it has some information saying that should be num-T. Num-T, meaning all the types are num-T. Okay, are you with me? Then, look at that. This is var T. It's an option type. So option meaning nothing or something. Meaning this var T, T something, Ti, T1, T2, T3, whatever that is, that's either none or some. That does not have any information about its type or it should be the same with this type. And this type can be another var T, right? Do you see that? Because var T is also type. Var T, var T, var T like that. We may not like it. So what can we do? We need a function called resolve. Resolve. That's too complex. Please make it simplified. Resolve. Resolve takes a type, produces another type. And it takes a type and resolves any wrapped var T. Get rid of them. Get rid of the onion layers. 양파 껍질을 계속 벗겨요. var T 쓸데없는 var T 썸을 계속 벗겨요. Until we get to the point. So type could be num-T, arrow-T, var-T. If it's already num-T or arrow-T, then we know what it is. Just return it. If it's var-T, let's get rid of those sums, right? var-T and none, it does not have any information. Return it as it is. var-T with sum, that should be the same with this type T. Recursively resolve that T. Are you with me? Okay, then let's see. When type tau is just T, this case, right? Just T. Resolve T is just T, right? When type tau is var T with some information, right? What do? Resolve that information. Resolve that num-T. So resolve that thing is num-T. Okay, good. What about that? Tau1 is tau2 and tau2 is none. What can it do? Resolve T1, resolve this one. Okay, resolve var T sum, resolve T1, var T of sum, tau2, tau2. Finally, T2. Finally, when we have var T sum, tau2 and var T num-T, then what can you do? Resolve, go away. Resolve tau1 is going to be num, right? These are all helper functions so that we can talk about inference and type unification that we are going to discuss after the first break.